The ship had never left port, had never been struck by a torpedo, had never even carried cargo across open water, and it split apart anyway, its steel hull tearing across the deck with a sound witnesses compared to a rifle shot fired underwater. It happened again and again. Across American shipyards during the Second World War, dozens of Liberty ships, the mass-produced cargo vessels that carried the weight of Allied supply lines across two oceans, fractured without warning, sometimes while sitting quietly at the dock in freezing weather with no enemy anywhere near them. Naval engineers were baffled. The steel met every published specification, the welding met every inspection standard, and still the ships kept cracking, and nobody in the shipyards could explain why, until a woman working the quality inspection line traced the fracture pattern back to a detail almost everyone else had dismissed as irrelevant. This is the story of the inspectors who caught America's most dangerous wartime shipbuilding flaw, a structural failure that threatened to undermine the entire Liberty ship program at the exact moment the Allied war effort depended on it most. The Liberty ship program represented one of the most ambitious industrial undertakings of the entire war. The United States needed cargo vessels in numbers no shipyard had ever attempted to produce, and it needed them fast enough to replace ships being sunk by German U-boats faster than traditional construction methods could ever match. The solution was a radical departure from decades of shipbuilding practice. Instead of riveting hull plates together individually, a slow process requiring immense skilled labor, American shipyards adopted all-welded construction, fusing steel plates directly together in continuous seams that could be assembled by newly trained welders working in parallel across prefabricated hull sections. The approach worked spectacularly in terms of speed. Shipyards that once took over a year to complete a single vessel began turning out finished Liberty ships in weeks and in a few extraordinary publicity demonstrations in a matter of days. The production numbers were the pride of American wartime industry, a symbol of manufacturing capacity that Axis planners had badly underestimated. But welded construction introduced a structural vulnerability that riveted ships had never faced in the same way. A riveted hull was built from overlapping plates joined at discrete points, and any crack that formed in one plate was naturally contained by the joint, unable to spread past the rivet line into neighboring sections. A welded hull was fundamentally different. The continuous welded seams created a single, unbroken steel structure across the entire ship, which meant a crack that started anywhere in that structure had a clear, uninterrupted path to travel. If the steel itself became brittle under the right conditions, a fracture that began as a small flaw could propagate across an entire hull section in seconds, tearing through weld after weld with nothing to stop it. This phenomenon, brittle fracture, occurred when steel that behaved normally at moderate temperatures lost its ability to absorb stress gradually and instead failed suddenly and catastrophically once temperatures dropped low enough, a threshold that varied depending on the specific chemical composition of the steel batch involved. Quality inspection on the Liberty ship production lines was staffed heavily by women entering industrial labor for the first time as men left shipyards for military service. These inspectors were responsible for examining completed welds, checking hull plates for surface defects, and verifying that construction met naval specifications before a ship was cleared for launch. Much of this work involved visual inspection and precise measurement, checking weld bead consistency, looking for surface porosity or incomplete fusion, and cross-referencing completed sections against engineering drawings that specified exact tolerances for every joint in the hull. The work required sustained attention across long shifts, examining hundreds of feet of welded seam on every vessel moving through the yard, catching defects that could compromise structural integrity long before a ship ever reached open water. When Liberty ships began fracturing in early operational reports, the initial investigations focused on the most obvious suspects. Engineers examined welding technique, inspected for gas porosity within weld beads, and reviewed whether individual welders had deviated from prescribed procedures. None of these explanations held up consistently across the failures being reported. Ships built by different yards, welded by different crews, using materials that had all passed standard inspection, were fracturing under broadly similar conditions, a pattern that pointed toward something more fundamental than individual workmanship. One inspector working the quality control line began cross-referencing failure reports against something the initial investigations had treated as background noise rather than a meaningful variable. The specific steel mill that had supplied plating for each vessel involved in a fracture incident, and the ambient temperature recorded at the time each failure occurred. The pattern that emerged was consistent in a way individual welding errors could never explain. Fractures clustered overwhelmingly around ships that had experienced cold weather conditions, either during construction, during dockside testing, or during early voyages through colder waters. More significantly, the pattern correlated with specific batches of steel plate, suggesting that variation in the raw material itself, not the welding process applied to it, was the underlying cause. This observation ran directly counter to the assumption naval engineers had been operating under, that steel meeting published tensile strength specifications with steel that would behave consistently regardless of temperature. The inspectors' cross-referencing suggested instead that certain steel compositions, all technically compliant with existing specifications, became dramatically more brittle at temperatures well within the normal range Liberty ships would encounter operating in the North Atlantic. This distinction mattered enormously because existing quality standards for shipbuilding steel had never accounted for what metallurgists would later formalize as the ductile to brittle transition temperature, the specific point at which a given steel composition shifted from absorbing stress through gradual deformation to failing suddenly through fracture propagation. Two batches of steel could meet identical published specifications for strength at room temperature testing conditions while behaving completely differently once actual operating temperatures dropped closer to freezing. Standard inspection procedures at the time tested steel at controlled laboratory temperatures that did not replicate the cold conditions ships actually experienced at sea or at dock during winter months, meaning steel could pass every existing quality check and still carry a hidden vulnerability that would only manifest under conditions the inspection process never tested for in the first place. Bringing this pattern to the attention of naval engineering staff required inspectors to push their observations up through a chain of command that initially treated the correlation as coincidental, consistent with a broader institutional tendency to prioritize explanations rooted in individual workmanship or welding technique over explanations that implicated the fundamental material specifications the entire shipbuilding program had been designed around. Overturning that assumption meant presenting evidence detailed and consistent enough that it could not reasonably be attributed to chance, tracking failure incidents against weather records and mill batch numbers with enough precision to demonstrate a pattern too strong to dismiss. Once naval engineering accepted the connection between steel composition, temperature, and fracture risk, the response reshaped shipbuilding practice for the remainder of the war. New specifications required steel testing at low temperatures specifically designed to identify brittle behavior before plates were approved for hull construction. Crack arrestor plates, sections of more ductile steel, riveted rather than welded into strategic points along the hull, were introduced specifically to interrupt fracture propagation, essentially reintroducing the joint-based crack containment that riveted ships had possessed naturally, but applied surgically at the specific structural points where analysis showed fractures were most likely to originate and spread. These modifications did not eliminate every failure, but they dramatically reduced the frequency and severity of fractures across the remaining years of Liberty ship production, allowing the program to continue at wartime production speed without the catastrophic structural risk that had emerged from operating conditions nobody had originally accounted for. The full scale of the brittle fracture problem is difficult to overstate in terms of what was actually at stake. Nearly 3,000 Liberty ships were built during the war, forming the structural backbone of Allied supply lines across the Atlantic and Pacific. A systemic failure in the steel supply feeding that program threatened not just individual vessels, but the entire logistics network the Allied war effort depended on to keep troops supplied, equipped, and reinforced across every active theater. The engineering community's eventual understanding of brittle fracture behavior, developed directly in response to this crisis, became foundational to modern structural engineering and metallurgy, influencing steel specifications and welding practice for decades after the war ended, in shipbuilding and far beyond it. What makes the identification of this flaw particularly notable is how directly it depended on inspectors doing work that extended well past the narrow technical boundaries their job titles implied. Cross-referencing failure incidents against weather data and mill batch numbers required treating quality inspection not as a checklist exercise, but as an ongoing investigative discipline, willing to question whether the specifications themselves, rather than the workers executing them, might be the actual source of a systemic problem. That kind of analytical initiative rarely appeared in official wartime accounts of shipbuilding achievement, which tended to celebrate production speed and tonnage, delivered rather than the quieter, more technical work of figuring out why ships were failing and fixing the underlying cause before the problem became catastrophic on a wider scale. The Liberty ships that avoided the fate of their fractured predecessors did so because someone was willing to look past the obvious explanations, cross-reference data nobody had thought to connect, and push an uncomfortable conclusion up through an engineering hierarchy that initially resisted it. The ships kept sailing, the supply lines held, and the specific reason a generation of American cargo vessels stopped splitting apart in cold water traced back to inspection work that history rarely bothered to credit by name. Every dusty page still hides a name history forgot to remember. Follow Iron Women Archives, and let's keep prying those pages open, one forgotten woman at a time.